I am Boris Albrecht. So thank you for the introduction. I am a quantum hardware engineer at Pasqal. And I joined, I am part of the R&D team. I joined the company because I wanted to play a role in the rapid progress of quantum computing technologies and see short-term results and applications of my work. And I have to say that this has been a great choice, actually. So, okay. Today I will speak about tangible quantum computing benefits. So first, I will give a short history of Pasqal, which is a company that emerged from the great French tradition of physicists. Then I will present our platform and our full-stack solution. Third, I will present two first-of-their-kind commercial results, one in partnership with a company, showing tangible live business results today. And finally, I will lay out our technical roadmap and tell you how you can partner with us. So, Pasqal has been founded in 2019. Amongst the funding members are Georges-Olivier Raymond, Alain Aspect, and Antoine Brouez. And I think neither of them need more introduction from me. So the company is now a full-stack international organization with international presence in Europe, North America, and the Middle East. And we are now counting over 150 scientists and engineers. Our technology is backed up by 4 decades of great scientific and engineering deliveries. So I will now present you our platform and what we offer in terms of a full-stack solution. So the experimental platform is neutral atoms for quantum computing. So we have an environment in which we isolate qubits. The environment has several advantages. So it is a room temperature environment. It has a quite low energy consumption, only a few kilowatts. The core of the system is an ultra-high vacuum chamber, where the pressure goes down to 10 to the minus 11 millibar, which is extremely low, but nonetheless, it's a standard vacuum technology today. And finally, we have a very well controlled environment in terms of electrics and magnetic fields, which is ideal to have very well isolated qubits. So the qubits themselves are encoded on neutral atoms, which are inherently identical, and this is a great advantage for scalability of our system. They are fully controlled by laser light in 3 aspects mainly. So we can manipulate individual qubits in displacement and placement. Strong interactions between qubits are mediated by light via Rydberg interactions. And we can detect efficiently even single qubits by camera imaging. So on top of that, our platform allows us for arbitrary positioning of the qubits and even has a 3D capability. And finally, there are distinct sets of pros and cons depending on the atomic species which is chosen to encode the qubit. So on the right, you can see some example of experimental data that we acquired on our quantum processing unit, which I will now call QPU. So at the top are 6 images. So these are simulations of antiferromagnetic states with 2 different geometries, a square lattice and a circular geometry. So to the left are loading of the qubits in the optical tweezers that we use to trap them. To the middle are the qubits after having been displaced in the desired pattern. And to the right is the result of the measurement. And below, this is an example of the training of a quantum machine learning algorithm with up to 50 qubits. And yes, the video works. So you can see this is a video from a live measurement. And the 2 images are before and after interactions. So now I will present our full stack solution. So we build from the hardware up to the software and applications. So I just presented you the hardware. The software and application includes turnkey solutions, a coding environment, but we also have a no-coding approach, which is called Pulsar Studio. And I encourage you to see a demo of Pulsar Studio at our booth in the exhibition room. Linking software and hardware, we have the middleware with an expanding set of quantum libraries, allowing to perform machine learning, solve differential equations, optimization, simulation. So we have already a number of customers and end users of our full stack solution. But we also have many collaborations in multiple sectors to develop industry-relevant applications. These sectors include energy, mobility, healthcare, finance, high-tech, and public sector. And in the following, I will present you 2 use cases, which we picked among several ones, one on risk management and one on toxicity screening. So I insist that these results are really first of their kind results, run on hardware, on our actual hardware. So, give me just 1 second. Yes. So the first result, sorry. The first use case, sorry, is about was a partnership with Crédit Agricole and Multiverse Computing, and is about credit risk prediction. So the problem is managing financial risk with loans. So when a company's credit rating falls from investment grade to below, it is called a fallen angel. And improperly rating fallen angel costs a huge amount of money to lenders, approximately $30 billion in missed revenues opportunities. So this has a very, very big market. So this rating is very computationally challenging, and there is no perfect classical solution to perform it. So we applied a quantum machine learning method to predict the deteriorating credit scores, and the preprint of this work is published on the archive. So I will give a bit more technical details about this method. So it is based on a quantum machine algorithm called QBoost, which we run on Pascal's 50-qubit QPU. I will tell you that this approach has very distinct advantages over the classical approach due to the imbalanced dataset and expensive solution space. So the goal of the QBoost algorithm itself is to train a strong binary classifier that can, in the end, tell us if a loan is going to be a fallen angel or not, basically. So the main advantage of the quantum aspect in this use case is the ability to handle hard optimization tasks much more efficiently than classical computers. So after running the algorithm on our hardware, it was benchmarked. We benchmarked the performance, against a state-of-the-art classical algorithm, which is a random forest search. And we show that the performances were already on par with the classical algorithm, but with very fewer initial learners. So the classical algorithm used was with 1,200 initial learners, and we were able to achieve similar performances with only 50 qubits. And simulation show that we can expect a clear advantage now against this same algorithm with hardware which we expect to be delivered within the next 2 years. So you can really take this message that we expect to deliver quantum advantage within the next 2 years for some applications. And these are first of their kind results which pave the way for quantum machine learning solutions. So now I will present you the second use case. So this use case was about toxicity screening. So we used yes. So the problem was evaluating the toxicity of chemicals based on their molecular structures, and this is a process that traditional methods can last up to 2 years and cost 200 million per successful drug in capitalized costs. So the difficulty is to store and classify massive data sets of objects which contain each many attributes. And the method commonly used is called a kernel method, where you encode the properties of all these objects in a matrix, and then the data themselves are encoded onto graphs. And then these graphs, so the kernel is applied to these graphs, and we can then classify our data within 2 classes based on similarities. So the neutral atom approach is very well suited to solve this kind of problems, which we can encode onto graphs. And I also have to say that this work has been published recently in PRA. So the method was to implement the quantum evolution kernel, which is a novel proprietary algorithm developed by Pasqal team. And we were able to perform a binary classification tasks on a biochemistry dataset. The dataset itself was predictive toxicity challenge on female mice. One of the advantages of being able to run simulations is, of course, that you avoid doing tests on real animals. And so we ran this on the QPU using rubidium atoms, so the same hardware as for the previous use case. And in the end, we showed that this quantum kernel is able to capture features that are invisible to classical kernels, such as support vector machine or size kernels. And it shows a significant speed up over competing quantum implementations. These results were benchmarked against several classical methods, and we were able to demonstrate on-par performances with the best classical kernels on real data. And on modified reliable data, we even are able to show an improvement. So after this, I will show you our technical roadmap and explain you how you can partner with us. So one very important message first is why it is very important to be part of the early adopters of quantum computing technologies. So according to the Boston Consulting Group, 90% of the profits may only be shared by 10% of the early adopter users. There are 3 kind of constraints here. So the talent is limited worldwide. The hardware is still very limited. And quantum use cases take time to develop. However, despite of this, so access to quantum talent and resources today is inexpensive, and pricing power will shift when quantum advantage hits. So it's very advantaging to join now. So our technical roadmap is the following. So first, I have to show you that there are 2 lines here. One shows the analog computing, and the other one the digital computing. And our platform with neutral atoms is very powerful in the sense that we can develop both approaches in parallel on the same platform without having to re-engineer the whole platform. So it will allow us, well, it already allows us to have near-term results with the analog approach. And while we move rapidly towards the digital fault-tolerant computing. Sorry. So today we are in the enterprise-grade analog computing era. So this means that using a quantum computer can achieve on par or superior results already compared to classical hardware. And this implies that we have to deploy quantum algorithm and hardware on live data in active workflows. So the next step is quantum advantage, and we expect to deliver this by 2024. which means that we should be able to perform calculations more efficiently than any of the best-known classical algorithms. So this is a huge step forward. And this will require us to scale the system to thousands of qubits and to develop even more performant quantum algorithms. And finally, in the longer term, our platform will allow us to reach the digital fault tolerance stage within a few more years. So I hope that I was able to convince you that it is important for you to partner with us already today. And at Pasqal, we are already ready for this with our full stack capabilities. So I will explain you how you can partner actually with us. So Pasqal developed the Quantum Adoption Plan, which is a plan in 3 stages, from exploration to industrialization. And I will insist only on the first step of the plan today, which is the exploration step, called quantum discovery. So this package includes access to quantum computers and emulators with 20 hours access to a 100-qubit QPU and access to a 40-qubit emulator. It also includes all the required middleware, as well as pre-coded example of quantum algorithms, and interactive tutorials. And finally, there is a support service with online learning, virtual support, and use case validation in collaboration with our experts. So this is very recent. Actually, it has been launched in March 2023. And if you want, you can request a demo on the link which appeared. So really, you should partner with us. And you can reach us at pasqal.com. And I also invite you to visit our booth in the exhibition. So as I said, there is a demo of Pulsar Studio. There is also a very nice demo with a virtual reality set where you can see our hardware. Thank you. And I have one last thing. So this year, as certain of you might know, is the 400th birthday of Blaise Pascal, who was a French scientist and philosopher. And he actually developed the first ever computing machine, which is called the Pascaline, so at the age of 19, quite exceptional. And so our company, of course, is named after him, except that we replace the C by a Q, as any respectable quantum computing company. And to celebrate this event, so Pasqal is planning something which will be revealed at Vivatech in June. And with this, I thank you.
Thank you, Boris. We may have time for one question at least, if someone has a question for Boris. All right, there is a question here. If you can bring a mic, or if someone speaks loud.
Boris, thank you very much.
Yeah, you are welcome.
I'm just wondering, like you mentioned about the discriminative models, like in machine learning, about the random forest and kernel techniques.
Yes.
Do you have any use case for the generative models, which is very interesting actually, as compared to discriminative? Because we are very well taken care with the discriminative stuff with the classical domain.
Okay, this is a very interesting question, but unfortunately I am not able to answer because I don't have the information myself, so I'm not part of the quantum machine learning team. Okay. But I will go back to you and I will be able to tell you more.
Perfect. Thank you.
Thank you.